Welcome everyone. So today we're going to discuss about classical mechanics, the Lagrangian and Hamiltonian approach. Now in classical mechanics, the Lagrangian and Hamiltonian formalisms are powerful reformulations of classical mechanics, offering an elegant way to find equations of motion, especially for complex system, by focusing on energy rather than forces. So now in Newtonian mechanics we focus on the forces and accelerations, but in case of Lagrangian and Hamiltonian formalism we focus on energy, which are scalar quantities. Both formalism describes the same physics, but this formalism gives a more abstract and simpler mathematical framework to solve physics problem of advanced levels. Okay, so now we're going to start our mathematical calculations of Lagrangian and Hamiltonian, but first we need to consider the generalized coordinates. So we're going to start with generalized coordinates. Generalized coordinates in classical mechanics are a minimal set of independent variables that fully describes a system's configuration, simplifying analysis by incorporating constants. So generalized coordinates are actually set of independent variables, just like the Cartesian coordinates x, y, z. Here we're going to use the generalized coordinates which are q1, q2, qn. These are our generalized coordinates. For generalized coordinates, they need not have dimensions of length, and they can be angle, distance and phases, etc. and they are adapted to constants. These are some key features of generalized coordinates, and we're going to consider some examples. So particle in plane, in case of particle in plane we use xy Cartesian coordinate. Instead of using xy we use r theta. So here we can consider that q1, q2 are our generalized coordinates. So q1 can be r and q2 can be theta. And similarly for simple pendulum, if we consider simple pendulum with a fixed length of rod L, then we can consider that theta, only 1 degree of freedom is needed, that is theta. So we can consider that as our generalized coordinates. So q as, we can consider q as theta. So in that case our x and y will be x equals to L sin theta, and we can write y as minus L cos theta. So in this way we can use generalized coordinate instead of using Cartesian coordinates. So now these generalized coordinates are actually some powerful tools to consider the motion of constrained systems, and they are powerful tools for Lagrangian and Hamiltonian formalism also. So today we have discussed about the introduction of Lagrangian and Hamiltonian formalism in classical mechanics, and we also considered the generalized coordinates. And on our next class we are going to talk about the virtual work and D'Alembert's principle. Thank you everyone.